Welcome to our first question on mathematical induction. The assertion given or the proposition given asserts that 3 plus 6 plus 9 plus 12 plus up to 3n is equal to 3n into bracket n plus 1 all on 2. This assertion is just saying that if you observe the numbers, you can see that they are multiples of 3. It means that when you want to sum up the multiples of 3, no matter what the quantity, you can use the simplified formula on the left. For instance, sum of the first 4 multiples of 3. The first 4 multiples of 3. That would be 3 plus 6 plus 9 plus 12. We're going to have, here will be 9 plus 21. That will give us 30. What the assertion is saying is that we could have equally just used the formula and substitute 4, because we are dealing with 4 multiples of 3, the first 4. So 4 plus 1, all on 2. We're going to get 12 multiplying 5 on 2. And this will also give us 30. So you can see that we have arrived at the 30 with that expanded form. So that if you are asked to find the first 20 multiples, sum of the first 20 multiples, sum of the first 20 multiples. This proposition is saying that instead of less than the first 20 multiples, I could equally use 3n plus 1 over 2. And that's what we have to prove. And remember, no matter the number of multiples, the last term will always be 3n. For example, when we are less than the first 4 multiples, you can see that the last multiple is 3n. 3 times 4. If we want the first 20 multiples, the last one will be 3 multiplied by 20, which is 60. You can try and see. Lessen down the multiples of 3. The last term will be 60. So this is a generic statement that has been written. General statement that tells you that you are adding 3, 6, 9, 12 up to the last term. And the last term will be in the form of 3n. It is going to be 3 times n. So if you have less than 5 multiples, it will end at 15. 3 times 5. If I want the first 10 multiples, the last term is going to be 30. You can try it and see. The last term is going to be 30. I'm trying to just explain the proposition for you so that you understand. All this is not part of the induction process. Good. Now, once that you understand the proposition, now let's go through the inductive process. If you are to prove this by mathematical induction, you have to prove this by mathematical induction. The first stage is the base case. We have to prove that it is true at the base level. And this one, the base level is when n is equal to 1. When n is equal to 1, the base level. So we have to prove that it is true at the base level. So when n is equal to 1, it means the first multiple, only one multiple, the first multiple with 3. Let's see whether when we put the 1 in the formula, we are going to arrive at the same thing. So 3 into 1, then 1 plus 1 over 2. Then we are going to have 3 multiplying 2 on 2. We see that we are going to get the same 3. So it is true for the base level. So when the base level is true, you move to the hypothesis stage. You write your inductive hypothesis. Inductive hypothesis. The inductive hypothesis is when you test, you write the assertion, the proposition, how the proposition asserts when n is equal to k. So assuming n is equal to k, the first k multiples of 3. We don't know the value of k. K can be 10, can 20, can be any number. So the first k multiples of 3 will be 3 plus 6 plus 9 plus 12 plus plus 3k. I said if k is 20, then the 3k will give us the last multiple, as I've explained earlier on. Good. Then the right hand side will be 3k, k plus 1, all on 2. So this is our inductive hypothesis. We are going to prove that if n is equal to k is true, then n is equal to k plus 1 should also be true by using this inductive hypothesis. So let's look at when n is equal to k plus 1. N is equal to k plus 1 means we are going to find the k plus 1th term. So if we are to expand this is going to be 3 plus 6 plus 9 plus 12 plus plus 3k plus 3k plus 1. Because if k is, let's say 10, if the value of k, I'm just making an assumption. If k is 10, that means this hypothesis is saying the first 10 multiples of 3. And then the k plus 1 will be what? 11. So that will be the first 11 multiples of 3. And the first 11 multiples of 3 will contain the first 10. That is why we are seeing the 3k here. The first 11 multiples of 3 will contain the first 10 multiples of 3. I hope you get it. So, but in this case, our last term will be what? 3 into bracket k plus 1. Good. But k is not 10. That is just to illustrate for you to understand. So let's go to the right hand side. The right hand side is that we could have used the formula straight away. So that will be k plus 1. Then into bracket k plus 1 again. All on 2. Okay, so let's continue simplifying. This will give us 3. Let's just write everything again. Plus 12 plus plus 3k plus 3k plus 1 is equal to, let's simplify this bracket. We are going to have 3k plus 1 k plus 2 all over 2. Now remember, we are going to use the hypothesis to prove the case when n is equal to k plus 1. So if you look at our statement here, from here up to here is our inductive hypothesis. What I am putting in the bracket, in the square, is our inductive hypothesis. And that simplified to 3k, k plus 1 on 2. So we can drop that one and just write 3k, k plus 1 or on 2. I'm repeating again. What is in bracket here is the same thing as what is here. If you can see that, then we can say if this expression 2 is equal to this one, then we can equally leave this one and come and put it in place here. So that's what we are trying to do. Okay, so we have lifted that one and placed it there. So that's the inductive hypothesis. So what is now left is to prove that the left-hand side is exactly the same as the right-hand side. So we are going to use that based on our skills in mathematics, our skills in algebra. We apply all our ingenuity, all our knowledge that we know in mathematics to manipulate this expression to look exactly like this one. So I am going to copy the left hand side only. So this is 3k into bracket k plus 1 all on 2 sorry, plus 3 into bracket k plus 1. We are going to add them using addition of algebraic fraction. So this is over 1. The LCM here is 2. 2 goes into 2 once. So to multiply the numerator is the same thing, k plus 1. Then 1 goes into 2 times. So to multiply the numerator, it will be 6, k plus 1. I can factorize the bracket out, k plus 1 out. So I have k plus 1, then 3k plus 6, all on 2. Then the second bracket, the 3k plus 6, I can factorize the 3 out. Then I have k plus 1, then 3k, sorry, the 3 has been factorized out here, so you have k plus 2, all on 2. When you factorize the 3 out here, you're going to get k plus 2. But I have just written the 3 at this side. So take note of that. Don't get confused. The factorization was actually done in this bracket, but by convention, you have to write the 3 outside the bracket here. Good, you can't write it in the middle here. Sorry. So now let's compare our final expression to what we had in the previous page. You can see that this is exactly the same thing as what we have. Then what is left is now to draw a conclusion. So we conclude that the statement or the proposition 3 plus 6 plus 9 plus plus 3n is equal to 3 into bracket n plus 1 all on 2 is true for n greater or equal to 1. That is all. So we'll look at another question and look at how we'll tackle that. Remember, mathematical induction, the proving stage, we don't have a precise steps. We don't have a lay down procedure. When you have gotten your hypothesis and you have gotten the expression for n is equal to k plus 1, all that is left is for you to use your hypothesis to prove your case when n is equal to k plus 1. And you are going to apply all your mathematical skills, ingenuity. There's no lay down procedure. Only that the steps you'll be following should be laid down accepted principles in mathematics. You apply already known principles, axioms, theories that you know in mathematics. There's no lay down procedure. Take note of that.